am Narayanan and this is my companion video for my TA application at UCSD. I will be going over the Scale Invariant Feature Transform, which came into picture when approaches such as edge detection and corner detection were not able to give us transition, rotational as well as scalar invariant features. So SIFT essentially works in two steps. Firstly, we can use it to detect locally distinct points, which are known as key points, right? And then these can be used to calculate descriptors, right, which can then be used to match these key points across two separate views. So now we'll go over the algorithm for the key point estimation. So firstly, we'll create an image pyramid, which basically means creating the image at different scales. So if this is your original image, then this is your original image. This is a slightly smaller version of the image. This is a slightly smaller version of the image. So yeah. So then the next step is to apply Gaussian blurring to each of the images at different smoothing scale parameters. So what that would basically mean is you take this image, you put it here. So this is your original image. Then this is your image Gaussian blurred with the parameter sigma. This is your image Gaussian blurred with the parameter k sigma. This is your image Gaussian blurred with the parameter k squared sigma with k greater than 1. And so all these images are of the same size, which is this size, right? And they are increasingly blurred. So now the next step is to take a difference of Gaussians. So basically take the consecutive differences. So difference between these two, difference between these two, and difference between these two. But why? Why are we doing the difference of Gaussians? So the main reason for this is that it acts as a sort of a band pass filter, where the difference, so here where the blurring is a little minimal, the more fine-grained features would pop up over here, whereas here where the blurring is quite large, more large-scale features will pop up over here, right? So now, as we have the difference of Gaussians over here, right, we will now calculate the extrema points. How we'll calculate the extrema points is we take these three layers, for example, right, and we'll see if this point x in the k sigma layer is an extrema point or not. So we compare this point with its neighbors here, so these 8 points here, and we'll also compare it with the 9 points at the upper scale in the blurring and the lower scale in the blurring, right? And if it's in if the comparison can show whether this particular point is an extrema point or not. So now we come to the fourth step. Now this fourth step is essentially required because the difference of Gaussians gives a higher response to edges. Now edges are not good because you can't localize along an edge. You can localize well orthogonal to the edge, but you can't localize along the edge, right? So edges have to be removed. So the way we do that is we take the ratio of the eigenvalues of the 2 cross 2 Hessian matrix imputed at the key point location, right? So now the Hessian matrix essentially encodes the curvature information along a particular point, right, and in all directions, and S transpose HS gives you the curvature in the direction of the vector S, right? So now assuming S is a unit vector, then this thing is bounded by the minimum and maximum eigenvalues, right? So once we take the ratio of the maximum and the minimum, right, if the point belongs to an edge, then the minimum eigenvalue would be quite low along the edge, right, and the maximum eigenvalue would be quite high and it will be orthogonal to the edge. So this ratio would explode, and so therefore we place a condition that if this ratio is greater than 10, we say that that point belongs to an edge. Now this is just a hyperparameter that you can set, right? So yeah, this way we remove all points that belong to edges. Now we come to the key point descriptor calculation. This is just a simple histogram of gradients calculation. If we are centered along here, we calculate gradients for each pixel, we place them into the histogram here, and so each histogram is a 8 dimensional vector, right? And in the paper they take a 16 cross 16 patch, right, and each 4 cross 4 patch is analyzed. So 8 orientations, 16 4 cross 4 patches leads to 128 dimensions. So 128 dimensional feature descriptor. R is your orientation information which is needed. So for example, if you rotate this image, then your vectors will go into the wrong bin. But if you have the R, the orientation, which is essentially the dominant gradient that is there, then you can correct your feature vector according to that, right? Then you have your scale and you have the location on the image. So this entire thing is your feature descriptor for the key point, and that concludes the SIFT algorithm.